Suppose R and S are relations from A to B. Must the following be true? Justify your answer with a proof or a counterexample. Alright, if R is a subset of S, then R inverse is a subset of S inverse. Well, let's sort of write down an example and see if we believe this or not. Let's just make up relations R and S. So maybe for simplicity we could have A and B both being the set 1, 2, 3. Okay, so R and S will be just relations on this set, relations from this set to itself. And maybe R will have a couple ordered pairs in it. 1, 2, and how about 1, 3? So that will be my R. And then S will contain those, but another one as well. Okay, 2, 3, how about? So S has R as a subset. And then we're wondering about R inverse and S inverse, and we can easily write down what the elements of those sets are. R inverse, we just switch the order, right? It contains 2, 1, and that's a 3, 1. So there's R inverse, and then S inverse contains all three of these with the order of the coordinates switched. So it contains these same two elements as well as 3, 2. Okay. And so that's pretty convincing that R inverse is going to be a subset of S inverse, right? If you just change the order of all the coordinates, then it's still going to work out just fine. So I think this is probably true. We should try to prove it. And let's just real quickly say, what's the idea of the proof here? Basically, we're supposed to prove that this subset thing's true. So, what if we just take an element CD of R inverse? All right, well, then we know that DC is in R, and because of our assumption, that implies that DC is in S. And if we rewrite that, we get that CD is in S inverse, which is our goal. Okay. So if you see that and you can take that and write a proof, you might not even need to do the table of givens and goals, but let's go through it anyway, just for practice and clarity. So we have a couple of relations, and we have this conditional as our goal. We'll prove that by direct proof. And then we have a couple of subset statements, so we'll write out definitions of those. And let's see, R and S are relations from A to B, so we know that their elements are going to be of the form ordered pair AB, so I can write it that way. And then over here, these are relations from B to A. But I'm going to go ahead and use some different letters just so I don't get confused here. C and D. And then, okay, we'll let C and D be arbitrary and to do direct proof to bring over a new given. Right. And then, all right, as we said, if before CD is in R inverse, then DC is in R. And that tells us which instance of our universal we should use, right? The DC. So if DC is in R, DC is in S. We can combine those using modus ponens to get the DC is in S. And that gives us our goal, right? CD is therefore in S inverse. So that's basically what we said a moment ago, but written out a little more carefully. So what do we have here in our proof? We are doing direct proofs, so we suppose R is a subset of S and prove R inverse is a subset of S inverse. And then we said let CD be arbitrary, and in fact let it be an arbitrary element of R inverse, and we'll show this. Okay, and from there, well, first of all, we said, all right, that means that DC is in R. So let's just state that. We know that DC is in R. And that told us which instance of this statement to use. And this came from where? That was the R being a subset of S, right? That got us there to here. And then these two, yeah, these two combine to get us that DC is an S. So we can say, oops, got some funny things going on here. Let me see if I can iron this out. Okay, because R is a subset of S, this, meaning what I wrote in my previous line, implies that DC is an S2, and that gives us our goal, right? This takes us to CD in S inverse, which was our goal. Therefore, CD is in S inverse. Okay.